Hi, everybody. This is notes on spring force and Newton's third law. So, starting with spring force, we are going to talk a little bit about that lab that we completed in class. If you recall, we had a spring with a little mass attached to the end of the spring. We were putting on different amounts of mass, calculating the force of gravity that we were applying from the mass, and then measuring how much that how much the spring stretched out, right? So, because we placed the mass on the spring and allowed it to come to rest, if we were to draw out the free body diagram, it would look something like this. We'd have force of gravity holding the mass down, and then something holding it up, right? We know it's got to be something holding it up because it's not moving up or down. In this case, it's not tension. A lot of people think it would be tension, but that's for ropes, strings, cables, things that don't stretch. Spring stretches though, right? So let's call it spring force. We could also call it elastic force. Another term for spring force is elastic force. I just call it spring force. But we know that these two forces are equal to each other because the object's not moving up or down. Okay. So then for the lab, I told you to graph on the x-axis, we put force of gravity, and on the y-axis, we put how much the spring stretched out, right? So for the purposes of us talking about this spring force here, instead, let's put spring force on the x-axis, because I know it's equal to force of gravity. So in the lab, as you were increasing force of gravity, you were also increasing spring force. Okay, and then on the y-axis, we're going to put how much it's stretched. We're going to use the term displacement to represent how much the spring has stretched, which kind of makes sense with what we know about displacement, right? It's how much, it's the difference between its starting point and its ending point. So we'll call it displacement, right? Okay, so if we take one set of data for one spring, it's probably going to look something like this. A linear relationship, we could also call this directly proportional. So if we're going to build an equation here for spring force, we can say that as spring force goes up, so does the displacement of the spring, right? Because that's what our graph says back here. As one goes up, so does the other, at the same rate. But this was not the same for every single spring, right? The difference between the springs were that they had different slopes. So, just like we did with the force of friction equation, we need to add an additional part of this equation to account for those different slopes. A coefficient that we're going to put in front of delta x that we are going to call spring constant. Spring constant. It is essentially a measure of how much force is required to stretch the spring. It comes in units of newtons per meter, and unlike coefficient of friction, there is no set number that it's going to be between. It's going to be a positive number, but it could really be anywhere from 0 to infinity. Okay, this equation actually has a special name. It is called Hooke's law. It's named after Robert Hooke, who discovered a lot of things back in the 1600s, but this was one of his contributions. So all stretchy objects, all elastic objects, so springs, bungee cords, rubber bands, fit into one of two categories. They are either Hookean or non-Hookean. If they are Hookean, then they follow this trend here, a direct proportionality between spring force and displacement. If they are non-Hookean, then they would not follow this trend. They maybe would look something like that, where it is more of an exponential relationship between the two. However, pretty much all of the all of the springs we are going to deal with in this class will all be Hookean. Okay, a little bit more on spring force. Here I have a picture of the same spring. In the middle here, This is the resting state of the spring, otherwise known as the equilibrium. So all springs want to essentially stay at their resting state. They have a certain length that they are comfortable being at, and they want to stay there as much as possible. However, people will stretch and compress them, and when they do, they are going to do their best to get back to equilibrium. So let's say that somebody is applying some force here to the right. Well, the spring wants to go back to its resting state, so the spring force will point to the left. I'm going to label that as a negative force because it's pointing to the left. That'll come up in a second here. Down here on the bottom image, the spring is being compressed by some applied force. So it is going to point, the spring force is going to point to the right, back to its equilibrium. While we're at it, why don't we go ahead and label our displacement of our spring, so the distance between the resting position and where it is stretched to, or the distance between the resting state and where it was compressed to. Now notice here on the bottom one, that has a negative displacement because it is being compressed. It is being squished to the left, okay? So on the top example, I have a positive displacement, but a negative spring force. And on the bottom example, I have a negative displacement, but a positive spring force. Those two things will always point in opposite directions. Spring force always points in the opposite direction of the displacement. Okay, let's use the spring force now. Here's an example problem. I have a mass attached to a spring, which is attached to the ceiling. The spring is initially 0.2 meters long, and then it gets stretched out to a total length of 0.5 meters. The mass is 3 kilograms. We're trying to find the spring constant of this mass, so let's do that real quick. We start by drawing the free body diagram. I would always recommend drawing the free body diagram for any problem first. So I have force of gravity down, spring force up. I know that this block is at rest, so those two forces must be equal. Well, that seems like a good place to start in terms of solving for this spring constant. I know that these two forces are equal, so I think they're going to help me solve for that spring constant. Spring force is K times delta X. Force of gravity is M times G. So I think we can start solving for this here. Delta X, in this case, it's not 0.5, it's not 0.2, but the difference between those two. It's the difference between the resting or equilibrium position and how much it's been stretched. So here, our delta X will be 0.3. Equals 3 times 9.8. So I get a K value of 98 newtons per meter. Okay, here is a tougher example problem. Here I have a block attached to a spring on a ramp, and that spring is attached to kind of a wall built on the ramp here. And so what we've done is we've placed this mass on the spring and allowed the mass to come to rest, okay? So it is motionless sitting there on the ramp. I have a spring constant of 500 newtons per meter. I have a mass of 30 kilograms. I'm trying to figure out how much this spring needs to stretch in order to keep my object in place. So let's start by drawing the free body diagram, like always. I have force of gravity pointing down. I have normal force perpendicular to the ramp, and I have spring force parallel to the ramp, up the ramp. Now, as with all ramp problems, I'm going to adjust my axis so that I only have one force at an angle. So this is me pretending like I am standing on the ramp with the block. This will be my new x-axis. This will be my new y-axis. Let me redraw that out here. This is what that free body diagram looks like with the adjusted axes, okay? So normal force points vertically up, spring force points to the right, and force of gravity is now 60 degrees kind of to the bottom left there. Because force of gravity is on an angle, I got to find the components, so I have FGX and FGY. To solve for the displacement of this spring, I'm obviously going to need spring force. And here I can see, because my object isn't moving based on my free body diagram, that the X component of gravity and spring force are equal to each other. My object's in horizontal equilibrium, so the forces pointing left and right must be equal to each other. Since I have one of each, that means that they're just directly equal to each other. The spring force equals the force of gravity in the X direction. I can swap those out with their equations. So I have the equation for spring force over there on the left, that is spring constant times delta X. And then force of gravity in the X direction is the total force of gravity, or mg, times sine of the angle theta. Now I plug in my numbers. K is 500, M is 30, G is 9.8, theta is 60. I solved for the right side. I got 254.61 divided by 500. I got an answer of 0.51 meters. Okay? All right. Let's talk about Newton's third law. Newton's third law is one that you've likely heard before, but the definition I give for it is a bit more scientific. Newton's third law says that every action force has an equal and opposite reactive force. Okay? So every force ever will come in a pair where you have that action force and then the reactive force is pointing in the opposite direction but has the same magnitude. Let me show you an example. Here's a picture of a guy. He is pulling a sled with a big rock on it. So let's label some of these action and reaction forces. Here is an action force. We'll call this, so the guy is pulling on the sled. So we'll call this the force of the person pulling on the sled. P on S, person on sled. Okay? Well, there is an equal and opposite reactive force. So that must mean that the sled is pulling back on the guy. So this is the force of the sled on the person. Okay? Let's say maybe there's friction. If the guy is going to the right while he's pulling this sled, then friction must point in the opposite direction of motion. So that's to the left. So this is the force of the ground on the sled. Well, then that equal and opposite reactive force would be pointing to the right. And it is the force of the sled on the ground. So the ground is pulling back on the sled, and the sled is pushing forward on the ground. Or you could talk about the force between the guy and the ground, right? The guy, when he's walking forward, right? Well, when you take a step, you're actually pushing backwards with each step. Your force is backwards from the direction you're walking. So this is the force of the person on the ground. And that equal and opposite reactive force, pointing the forward direction, that's what actually causes you to move forward. This is the force from the ground on the person. It's because of Newton's third law that you're able to walk forward at all, right? You push back on the ground, so the ground has to push back on you, and that's the actual force that's causing you to move forward when you're walking. Okay? Now, key takeaway here. Sometimes people get confused. They're like, wait a second, if I have a action force and a reaction force, doesn't that mean that all of my forces will always be balanced? Will I always have zero net force and no acceleration? Well, no, of course not. We know things accelerate because there's a net force. And the reason is because those equal and opposite forces act on different objects, right? Back here, it is the force of the person on the sled. So that force is being enacted on the sled. That would be drawn on the sled's free body diagram. And the force of the sled on the person, that force will be added to the free body diagram of the person themselves. So, equal and opposite forces act on different objects. Okay. And then we have these types of problems which are related to Newton's third law. So over here on the left, I have two blocks on a table, block A and block B. The coefficient of friction between the table and the blocks is 0.18. And somebody's pushing on block A with 650 newtons of force. Okay. Over on the right, we have kind of our goals, what we're trying to solve for. We are going to try and find the acceleration of the system. We are going to try and calculate the force each crate exerts on the other. And we are going to repeat that process, but reverse the crates. Okay, so before we get to any of that really, let's start by looking at the free body diagrams, okay? So I'm going to draw a free body diagram for, well, you know what? Let's do a free body diagram for the system as a whole. We'll do a free body diagram for object A and a free body diagram for object B. Okay, so free body diagram for a system as a whole. Let's draw a box around our system. That would be these two blocks here. Okay, so what kind of forces would we need? Well, there's definitely force of gravity pulling the system down, and there's normal force pushing the system up, and those two are balanced because I'm in vertical equilibrium. I'm not crashing down through the table. Okay, we have an unbalanced applied force, we'll call it F, of 650 newtons, and we know that there is some force of friction holding it back. Okay, we'll need that for later. Let's talk about the free body diagram of just block A. Well, the easy ones are normal force and force of gravity. They balance each other out. The force F is pushing forward on block A, and there is a force of friction pulling back on block A. That's good for now. We might come back to that in a second, but check out B. Block B, again, has force of gravity and an equal amount of normal force and probably has a force of friction pulling back on it. But is block B being pushed by that force F? Not really, no, right? Because if you look at our diagram here, the force F is not touching block B. And we only really deal with contact forces other than force of gravity, right? So what is in contact with B that is actually pushing it? It's block A, okay? So this force here, I'm going to call it the force from block A on block B. Okay, well, hang on a second. That's an action force. I need an equal and opposite reactive force. So that must mean that back here on block A, the free body diagram for block A, there is an equal and opposite force from B on A. Now, back in the system free body diagram, we don't have that force because it is internal to the system. That force is acted upon and canceled out within that system. But looking at the blocks as individuals, it's still there. Okay, so let's go about solving for those practice problems. Start by finding the acceleration of the system. All right, well, shouldn't be too hard. We're going to do net force equals ma. We're going to say there is a positive force F, that's our 650 newtons. Force of friction is pulling back on the object equals ma. By the way, why don't I make sure I don't forget, that is the mass of the system, right? Mass of the whole system. So we have F minus, well, the equation for force of friction is mu times Fn. We know that Fn is equal to force of gravity in this case, so let's swap that out with m times g. M is going to be the mass of the whole system times g equals ms times a. I think I'm ready to plug numbers in here. Force F is 650, coefficient of friction is 0.18. Mass is the whole mass of the system, so let's go back and double check. That's going to be 65 plus 25, so that's 190 times 9.8 equals 190 times that acceleration of the system that we are solving for. Okay, so let's plug that into our calculators. Okay, so I plugged that into my calculator, divide by 190. I got an acceleration here of 1.65 meters per second squared. Okay, okay, good start. That is our acceleration of the system. Now it tells me for part B to solve for the force that the crates exert on each other. So that's going to be this F of A on B or F of B on A. Now I can solve for either one because I'm just looking for the magnitude of those forces. I know they're going to be equal to each other, equal and opposite forces. So I think it's going to be easier for us to solve for the force of A on B because there's just less forces acting on object B. So let's do that. We are going to use the Newton's second law, net force equals ma, for object B. So the net force on object B, the mass of object B. Well, I know the object is in vertical equilibrium, so I'm going to ignore those forces. I know they already cancel out. So I'm just going to focus on the horizontal forces acting on object B. Let's double check here. I have F of A on B and force of friction are my horizontal forces. So a positive F of A on B, a negative force of friction times the mass of B equals the mass of B times A. Now I don't think I mentioned this before, but because those objects are essentially right next to each other, the one is pushing the other, their accelerations will be the same and they'll be equal to the acceleration of the system. So that's what we're going to use for A. And I think we're pretty much ready to solve here. Going to swap out force of friction with coefficient of friction times normal force. And I know that normal force is equal to force of gravity here because it's in vertical equilibrium. So we'll do a quick swap there. And now I think we're ready to plug in some numbers. So F of A comma B minus coefficient of friction is 0.18. Mass of block B, let's go double check that real quick. That is 125 times 9.8 equals 125 times acceleration of the system, 1.65. So I multiply all those together. I'm going to add this product over there, and I'm going to get a force from A on B equal to 426.75 newtons. Okay, all right, so that is the force from each of those boxes. It is the force from A on B as well as the force from B on A. Okay, now for part C, the question is, what if those blocks were first, right? They were in different positions. Block B was first, then block A. Well, that would be pretty much the same exact thing as I'm showing here on the right, right? The system is 100% the same. The individuals are pretty much the same. All I would do is block B's free body diagram looks more like this, and block A's free body diagram looks more like that. So in terms of the mathematics, it's actually going to be almost exactly the same as this here. I'm going to solve for the the force from block B on block A in this reversed version. So I'm going to do this same exact math, essentially, but with using block A's mass instead of block B's. So let me just grab this equation here. I'm going to rewrite this. It's going to be all the same except block A instead of block B. So this is the force from block B on block A. I'm using the mass of block A because remember that is the one now that is in front. It's on the right in our picture. And it is the mass of block A times the acceleration of the system. So let's figure out what this one is. We've got, all right, so this is the thing we're solving for. Coefficient is 0.18, mass is 65, G is 9.8, M is 65, and the acceleration is still 1.65. Let's plug this into the calculator. So this time when I plug it into the calculator, I am getting an answer of 221.91 newtons, okay? So in this reverse world where block B is first and then block A, there we have a force between the two of 221.91 newtons, which kind of makes sense, right? Block B would need to push less on block A because it has less mass, right? So it doesn't need to push as hard as block A is pushing on block B to get them moving at that rate. Okay, that is spring force and Newton's third law. Hope this was helpful. I'll see you later.